Hi guys, let's continue with the previous topic. We're going to talk about database indexes and we're going to cover some more advanced scenarios. We're going to look at the join operation, we're going to look at sorting and grouping, we're going to see how the overall CRUD operations reflect our indexes, updating data. By updating, I mean every time we want to modify a data, what happens with the indexes. That's creating, updating, and deleting. We're going to talk about clusterization. We're going to cover some of the most popular indexing myths, and we're going to talk about index performance in general. These are more advanced concepts, so I suggest you first watch my previous video, which was released last month, about database indexes, if you haven't watched it already. And if you have done that, let's continue with this topic. But it's important to understand the anatomy of the index, how it works behind the scenes, what data structures it uses. So again, if you haven't watched my previous video, I covered that and I cover how to analyze execution plans. So today these are more advanced concepts and they are more difficult to analyze through demo code. So I'm going to give you advice and some pointers on what to look at considering all these operations, the join, sorting, grouping, and so on. And I'm going to explain how to eventually optimize them. But in terms of performance, these situations here and these operations are most probably they're rare. They're more rare than the previous examples I showed you in the previous videos. So keep this knowledge in mind, but keep in mind that also they're uh, rare enough and you may never need to optimize these operations in terms of a typical web application. So first, let's talk about the join operation. The join operation, as you may already know, processes two tables at the same time. If you have multiple joins, the engine, SQL Server for example, first joins two of these 3 or 4 tables, then calculates the intermediate results between these two tables, and then it adds the result from the third one. So for every join operation, we have two tables which are joined at the same time. If we have more joins, then it's the same process with some intermediate results. In SQL databases, there are three possible algorithms which a join operation may use. The first one is nested loops. Nested loops is just a regular for loop executed over one of the tables, and then another for loop executed on the other table. So this is the most slower version of a join algorithm because it needs to operate on the whole table with one loop and another loop for the other table and then merges the result. This kind of algorithm works with small sets, so if you run an execution plan and see that your join operation uses a nested loop, then it means that you don't need to optimize it. It should be fast enough. Usually, SQL Server has an optimizer. This optimizer, his job is to consider the best approach for your query. In one situation, the optimizer may decide to use one algorithm, depending on previous queries, depending on cache, depending on the dataset and how many entries there are in the table. and it may decide different options. So generally in SQL Server, if you see a nested loop, you don't need to worry about anything. You don't need to worry about an optimization, because that means that the optimizer decided that nested loops are good enough and the data is not that complex to join. So the nested loop is the easiest way for a table to be joined with another table, and it happens with smaller sets of data. So here we don't need to do anything specific. The second join algorithm is the superior algorithm in many cases. The whole idea is that it uses hash tables. First, the SQL Server loads all the candidate entries from the queries into a hash table. And the hash table is based on the join condition. So if you join by ID, SQL Server gets all the IDs and maps all the entries in the table to these IDs. And then when the hash table is constructed, the engine just probes the hash table, and we know that hash tables are very fast for finding by keys. So the whole complexity behind this algorithm is actually generating the hash table. If we're joining on a condition which is already sorted and is a hash table by itself, for example, if we have an index on that condition, the whole hash generating process is kind of skipped. So the whole idea behind that is that the complexity behind this algorithm is the construction of the hash table. When SQL Server generates these two hash tables for the two tables, then the join itself is very fast, because a lookup in one hash table and a lookup in another hash table is super fast. So this algorithm is superior in many of the cases. So if you have a moderate amount of data, more than 10 or 100 entries in the table, I'm talking about thousands, SQL Server will probably don't use nested loops, but it will use hash joins. And we can optimize hash joins in a way. If we see a hash join in our execution plan, we may decide to optimize it if we are not satisfied with the performance of a particular query, but more on that later. The third algorithm for join operations is the so-called sort-merge operation. First, SQL Server needs to sort the tables and then combines them like a zipper. So imagine this. If we need to join two tables on IDs, for example, the primary key from one table and a foreign key from the other table, the sort merge algorithm first will sort the first table by IDs and the second table by foreign keys. Then it will start looking for each row separately, and when it finds a match for the join condition, it will get them. This kind of algorithm is, let's say that it's fast enough, but the sorting is expensive. So the sort operation is more expensive than using a hash table, because building a hash table requires n amount of operations if we have n entries in the table. But for the sorting, the fast sorting algorithm is actually n log n. So it's faster to create a hash table if we don't have one than sorting the table. But here comes the trick. If we have the data already sorted, then the sort merge is faster. Consider the following situation. I'm going to use an Excel table to demonstrate some of the concepts. But if we have 1, 2, 3, 4, 5, 6, 7 in one of our tables, and then we have foreign keys which are more mixed, for example 7, 4, 3, 1, 2, I'm missing 6 and 5. So if we need to use nested loops, then we need to have n operations for this table and n operation for this table. So SQL Server needs to traverse all the elements here and then traverse all the elements here. So essentially our complexity will be n multiplied by n. Then if we decide to use a hash table, the hash table is faster because we already have a hash table for the primary key index. So this is essentially super fast and it's kind of already built in. So what we need to do is we need to get a hash table by the foreign key here. But the foreign key is also an index by default, so already it's fast to create a hash table. So if our join operations are based on foreign keys, which typically they're based on foreign keys, we don't have that much performance issue to build a hash table because foreign keys and primary keys are indexed by default. But if we need to join on something else, on another count, for example, then it will get harder. So the hash tables are very fast because when we have a hash table here and hash table here, we need n operations to match all the joint results. We need to get the entry from the second table, which has number 1 as foreign key, and that's super fast because we already have a hash table for that. So basically the algorithm will be something like n operations. For each entry here we will need searching here. Of course, it's with huge data sets, it's a little bit more complicated because here we may have multiple columns, we may have no values, we may have only 7 entries here and 100 entries here. So it will not be exactly n operations, but it's still faster than using nested loops, the most basic approach. And if we consider the third algorithm, which is sorting, first sorting the tables by our condition and then merging like a zipper, SQL Server needs to sort these elements first. And what does that mean? It means that it needs to execute n log n, an n log n algorithm over this table in order to sort it first and then try to match the values. So first it needs to say, okay, I have 1, 1, 2, 3, then I have 4, 2 5s, then I have 1 6, and then I have 7 and 1 no, which does not match anything from here. So SQL Server will start looking one by one. It will get the first row, it will search for ones. Is that a 1? Okay, let's join it. Is that a 1? Okay, let's join it. Then, is that a 1? No, so continue. That's a 2. Is that a 2? Yeah, join it. Is that a 2? No, that's 3, so let's continue here, and so on, exactly like a zipper. The expensive operation here is n log n because of the sorting. But that's not exactly a problem, because when we have an index, the index is already sorted. So with the sort merge algorithm, if we use a join on foreign keys and primary keys, these are already sorted for us. So what SQL Server needs to do is it needs to merge the columns, but it's more difficult if we make joins by other conditions, which include columns which are not foreign keys or primary keys. Then we may need to use some sort of optimization. So these are the three algorithms which SQL Server uses. We have nested loops, hash joins, and sort merge. For the nested loop, we don't need to optimize anything. Usually the nested loop is used with smaller sets of data which are kind of fast already. For the sort merge, if we're using columns that are already sorted because they have indexes by design are sorted, then SQL Server just needs to merge them, which is already fast enough. And the third case is when we have a hash join, which is already kind of fast algorithm, but we can optimize it. But how to optimize it? We don't need to optimize it by design, because usually when we have a query on the join operation, these are already hashed when we have primary key and foreign key. Because of the indexes, these are already hashed, so we no longer need to optimize them. What we can do is, when, and typically we have that situation, is when we need to join on something, but we need to filter it first. So imagine the following. We have a select operation from some table, we need to join it, and then after the join, we need to filter it. So consider the following situation. If we have to do that, these are already indexed, and these are fast enough no matter the algorithm. The slower part of the query is not the join itself, it's the extra filter we need to provide on the join. So if we have an extra filter and the column from that filter is not part of the join operation, like here, we are searching for salary, which is not part of the join condition. Then we can improve the query by adding an index on the salary. If the filter is part of the join condition, then it's no need to add an index. This is the rule. If we have a filter on a join operation and the filter is using a column which is not part of the join operation, then we can add an index on that filter. Of course, it's a good idea to do that when we have a lot of data. All of the optimizations I'm showing you here should occur after we find a bottleneck. So don't add indexes prematurely. Don't add indexes without seeing a performance issue first. So use SQL Server with its default indexing options, the primary key and the foreign key. Then as your application grows, and if you find that some query is a little bit slow, then add an index. I believe I said that in my previous video already, but that's more important. That's the most important part of any kind of optimization. Never do it prematurely. Every optimization adds complexity to your solution, and adding additional complexity means additional support for bugs, additional maintenance, and so on. It costs you more if you don't have the bottleneck. You don't need to optimize prematurely. So the rule with the join operations is if you have a hash join or a sort merge for that matter, you can add an index or the filter. The other thing to consider is if your execution plan shows sort merge, then consider sorting the conditions. By sorting, I mean adding an index, because the index is data which is already sorted. But in this situation, you need to have columns in the condition which are not part of any index. So add indexes only on the columns you don't have index for. If you want to optimize the memory footprint of this indexing operation, don't use the star. You can reduce the hash table size which is generated for your joins if you specify only the columns you need, but that depends on the situation, so it's additional optimization you may do. This is everything you need to know about the join operation. It uses 3 algorithms. Most of them don't need any optimization, and actually the optimization you can do is not from the join operation itself, but from additional filtering, like this. So in this query, an index on the salary column is a good idea if I have a lot of entries in my database and the query is slow. And for sorting, if the join condition is part of foreign keys or primary keys only, then you don't need to do anything about it. It's already sorted and it's already as fast as possible. Let's talk more about sorting, and I'm talking about the order by clause. The order by clause, first, sorting is super intense. Sorting is expensive because even the fastest algorithm produces n log n complexity. And if you have millions of records, sorting needs to fetch all the records in the database, then execute the sort operation on all of these records, and then returning the result. This is why it's more intensive operation, because sorting cannot be pipelined. You cannot get the first 10 elements, sort them, then get the next 10 elements, sort them too, and so on. Sorting needs the whole table written into memory, and with lots of information and lots of data and entries in your table, sorting becomes very extensive, very intensive operation, and that's not good. So the whole idea and the whole problem behind sorting is not that it's a slow algorithm, but more that you need the whole table fetched into memory. If you have millions of records, that's very problematic. How to solve sorting and how to skip the problem with fetching all the data into memory? Well, again, with indexing. As we already know, indexing is data already sorted and stored on the hard drive. So if we want to sort something, it's already sorted, we just need to read it. We don't need to execute a huge sort operation on the table. So if we add an index, this gives us the data already sorted. What's important though is that we need to have the correct sort order in some specific cases, because if we have for example all our data sorted by salary on the hard drive and it's in ascending order, that means that we can read it in reverse and get its descending order. So it doesn't matter in what order we store the index. SQL Server can read it both ways. But there's a specific scenario I will talk in a minute, in which sorting order needs to be correct, otherwise you will have performance penalties. But one thing to keep in mind is that the SQL Server Optimizer, as I already said, is considering all available options for your queries. So it may decide that it's faster to do a full explicit sort if it's more cost efficient than to read the whole index from the hard drive. So depending on table size, you may see explicit sorting in the execution plan, but you may see that it scans the index. So if the data is super small or there's a filter predicate, SQL Server may decide that, okay, I'm just going to execute the filter on the index and then I'm going to execute the sort, because after the filtering the dataset is not that big and it's completely okay to do an explicit sort rather than reading the index from the hard drive. So it depends, but having an already sorted data for your order by clauses is a good idea. What is important about ascending and descending sorting is when you have more than one sort operation. That's the only case in which you care about the order of the sorting. Because, as I already said, databases can read indexes in both directions. If we have the data sorted, they can read it in reverse and they will get the descending order. If they read it in the normal way, they will get the ascending order. So it doesn't matter the order. But when we have multiple sort columns, for example like this one and then this one, we need to get some data from a table, and this is wrong, this should be order by, and we want to order by the results first by hire date and then by salary. The hire date is in ascending order and the salary is in descending. Here, if we have two indexes, because we may say, okay man, I need to have my data already sorted, so let's create an index on hire date and let's create an index on salary. This way we have an index having the already sorted data by hire date and already sorted data by salary. We have just a multi-column index. That's cool, but we need the correct index order in this situation, because if our index stores the first column in ascending order and the second column in ascending order too, then the database needs to sort everything because the second column is in descending order. Even though the data is already sorted on the first column, the second column still needs to be sorted because it's not sorted correctly compared to the first column. So if we have multiple order bys, we need to have the correct sorting orders in our index. Imagine the following. If we go to our Excel table, let's say that we have a table which has an index and the first column is this one and the second column of the index is this one, where we have let's make it a little bit more repetitive like this, and we are going to mark the second column already sorted again in ascending order. So a multi-column index, the first column is sorted and the second column is sorted where the first column is equal. So we can assume that if the first column is equal, then the second will be sorted, like this one, like this one, like these two also. So if we say to SQL Server, order by column 1 in ascending order, and then order by column 2 in ascending order too, then SQL Server just needs to read the index, because it's already sorted in the way we want it to be. But consider this. If we have sorted first column and unsorted second column, then SQL Server needs to do explicit sort. He needs to he can read the first sort, and that's okay, but then it needs to execute sorting algorithms for the second column. For example, here, here, and here. So here, here, and here. It needs to execute a sort order, which is essentially an explicit sort, and in this situation our index is not working for us. It doesn't save us anything for this particular query. So what we can do is we can use an index which is sorted the way the query expects it, like this. Here we again need to have descending order, and here too. So if we change the index sort order to be ascending in the first column and descending in the second column, then this query will work. Also, keep in mind that SQL Server can read the index in reverse, starting from the end, continuing to the start. So if we write a query which needs the first column in descending order and the second column in ascending order, then it can still work without explicit sort. So if the direction is correct, or if the direction of the query is exactly opposite of the index, then the index can be used. Otherwise, it needs to do an explicit sort. So that's the important part of sorting. If we add an index and we have an order by clause for only one column, then everything is fine. But if we have more than one columns in our order by clause, let me fix that. If we have more than one column in our order by clause, then we need to have index with the correct index order, and the correct index order is either the same as the query or exactly opposite. So in this case, descending and ascending will work too if the index order is correct. So either the way the index is stored or the exact opposite. If some of these values is mixed, then SQL Server needs to execute an explicit sort. This is all about you need to know about sorting. Good. Let's continue to grouping. Grouping has two separate algorithms which are entirely different. So the first one is hashing. First, the database server creates a hash table for the group by condition and then aggregates all the results. That's the first option. The second option is sort group algorithm, which means first sort the table by the grouping key and then aggregate it. Because if we have already sorted table, it's very easy to group it by the sort order. Both algorithms do not use a pipeline execution, so it needs the whole table to be fetched in memory and then grouped by. So what we can do is we can improve the algorithm if it's a sort group algorithm. The same way we can improve an order by clause. Consider that a group by clause can be improved the same way as an order by clause. If we add an index on the group condition, then the sort will be already done by the index. So the whole thing the database needs to do is just execute the grouping over the already pre-sorted data. So if we want to optimize a group by option, and let me pause a minute and talk about when we want to optimize a group by condition. First, we need to recognize there's a problem in our query. Then we need to run an execution plan. I covered execution plans in my previous video. And we can see that the grouping operation is slowing down the query. If we can see that the grouping operation is using the sort group algorithm, and we see that it takes a huge amount of the query because the execution plan provides percentage of the queries. So how much time the query needed for grouping, how much time it needed for sorting, how much time it needed for joining, and so on. And if you see that the grouping is your bottleneck, then you consider optimizing it. Don't optimize just because Kenoff said that grouping by should need an index. That's not the case. Optimize only when you have a bottleneck and when you see that the bottleneck is exactly for the problem you're having, exactly for grouping, exactly for joining, and so on. So if you see that a join operation is taking too much, then it may be the filter predicate on the join operation, like we said earlier. If you see that the sorting is taking too much, you can add an index on the sorting column, or change the order of the index sorting, and so on. If you see a grouping that it's taking too much time for your query, then consider adding an index to optimize the sort group algorithm, and so on. So never optimize prematurely. But a group by operator and a group condition can be optimized the same thing as order by clause without thinking about the sort order, because it doesn't matter in grouping operations. In grouping operations, SQL Server doesn't care about the sort order. It cares to have a sorted list, but it doesn't matter which order is. So the order is not important for the grouping. Now, let's talk about updating data, and by updating I mean everything we do in our database which modifies our data. Let's start with inserting data. This is the most crucial and most affected operation from having a lot of indexes. So the more indexes a table has, the slower inserting data will be, because the database needs to keep all the indexes in correct order and needs to keep the trees involved in balance. What exactly balance means? Well, in short, a balanced tree or a balanced data structure means that it follows it means that it follows the best data structure possible for the operations we need to execute on that data structure. So if we have a binary search tree balanced, then it means that every search operation should be as optimized as possible. So the database needs to keep the tree balanced on every insertion or every deletion. In terms of performance, the first added index makes the greatest difference. Here is a graph which shows the amount of indexes and the execution time depending on the number of indexes. So the first added index makes the most difference. If we have a query which executes for as fast as possible for this amount of time, when we add one index, we can see that the penalty is huge compared to adding a second index, because this difference here is a lot less, maybe half, but that depends on the query, than no having indexes at all. So the first index makes the greatest difference, and that's important. So if we can keep our table without indexes, then insertion will be super fast. Now, of course, in a real-world application with real-world scenarios, tables without indexes is a bit of a dream. So consider this: if we have one indexes, there is no problem having a second one, because the penalty is not that great compared to adding a first index at all. But we should keep some rules in mind. First, the rule about redundant indexes. If some of our queries change and an index is no longer required, we should delete it, we should remove it, because inserting data will be faster. So always keep track of your indexes, especially if you need to insert a lot of data. Another option is when we need to insert a lot of data, when we need to migrate a database, or we need to we have a bulk insert, a huge bulk insert, then it's a good idea to drop all the indexes, to delete all the indexes on the table temporarily, and then when we insert all the data, to add the indexes again. This may be faster than inserting data while the indexes are still part of the table. So depending on the situation, you may need to drop the indexes and then return them back. But that's again a tricky situation, because if your application is live and running, you may have problems with other queries which use these indexes. So it's very difficult to give you an example, to give you a correct way when to drop indexes, but keep in mind that you should consider it depending on your situation. So first rule about inserting: never leave indexes that are no longer used, and this situation may occur if your specification of the app change. And consider dropping the indexes if you need to insert a huge amount of data. For example, it's the time of the year when you need to import a lot of Excels, or you implemented a cool new feature which allows the accounting team to upload all their Excels and reporting is automatically generated, something like that. And when you have that cool new feature, consider removing all the indexes before importing all the Excel files. It's really tricky situation, so it depends on the case. That's for inserting data. This graph is very useful to consider adding a second index, because the first index is the most difficult and the most problematic. Updating data is actually very simple, because when you update data, sometimes the columns are not part of the index. So if you update the salary column and the index does not contain the salary column, then the index doesn't need to be balanced, and that's completely okay. So when you update data, consider whether the data you are updating is part of an index. Then it will have the same penalty as here. The tree needs to be rebalanced. But updating data is easier because usually when we update data, the chances that this data is part of an index is not that huge. So it's a little bit easier considering the inserting data operation. Of course, you may still decide to drop the indexes temporarily when you are updating data, especially if you need to update lots and lots and lots of data. But it depends on the situation. With deleting data, the delete statement has a where clause which can greatly benefit from indexes, but there's a small catch. What it means to delete an entry for the database. First, the entry needs to be found and then it needs to be deleted. So if we have an index, the finding part will be very fast because the index will be helpful there. But then deleting will be slow because we need to rebalance again the tree. So the index is helping part of the delete operation, but it's slowing down the other part. So executing a delete statement without an index, so to remove the index for the table to execute a delete statement, makes sense only when we need to delete a large part of the table. If we need to delete the whole table, there's a separate truncate operation. I'm not talking about that. I'm talking about the delete statement. So if our delete statement needs to delete a single element or two or three, a very small portion of the table, then the index will help us, because finding these elements will be very fast and deleting them will not be that much of a problem. But when we need to delete a lot of entries, for example, one of our tables becomes very slow because it has millions of records, and we need to delete the older ones because we no longer use them, or we want to archive them in some other table. So what we need to do is we need to delete a huge portion of that table. Then in that situation, having an index will be very troublesome, because the index will help us finding all the entries, but then it needs to be rebalanced for each entry deleted. And that's a lot of rebalancing which needs to be done. So the conclusion about the delete statement is, if you have to delete a single entry or 2, 3, 4 entries, not a huge portion of the table, having an index on the where clause helps. That's the most important part. For this tree operation, inserting, updating and deleting, make sure you check your object relational mapper. If you're using Entity Frame or Dapper or whatever, make sure you check what kind of operations it generates, because you may need to add an additional index if the object relational mapper is not providing optimized queries. So make sure you keep track on how your object relation mapper inserts data. For example, Entity Framework, if you have bulk insert, it inserts every entry one at a time. And for every entry added, you need to rebalance the tree. And if you add 100 entries, you need to rebalance the tree 100 times, which is kind of a problem. So when your ORM is not generating the proper queries, you may need to write them by hand. But again, you need to follow the same rules when you insert, update or delete data. For example, the ORM, you may need to update only part of the data, for example, only the salary column. But the ORM may be not optimized and it may send an update statement for every column in your entity, even though you are changing only the salary. Then, no matter what you do, every time you will fire an index rebalancing. So if your ORM is not optimized for updating only the data you provided, like the old Entity Framework 6, the old Entity Framework 6 never sent only the columns you update. It sent the whole object to the database. And for the database, that means it needs to update all the columns, and that's slow. So check your ORM for these crude scenarios, because you may be thinking that you're doing the right thing considering the indexing rules, but the ORM may do something else. So Entity Framework Core is kind of okay, but nevertheless check it from time to time. Clustering data. I'm going to talk about clustering data. Clustering data means to store consecutively data close together. It means that when you search for one, for example, an entry with ID 1, it means that the entry with ID 2 will be closer on the hard drive to 1. This makes fewer input-output operations to the hard drive. So indexes help us with that. We just need to include all the columns we want from a single query. This will result in an index-only scan without touching the original table. So consider when you create a query to include all the columns from that query in the index. The only penalty you will have from that is bigger hard drive space, but with current hardware that's not a big deal. So you better have better performance than smaller hard drive storage. So always consider adding all the columns from a single query to be included in the index. This technique may improve the performance up to 10 times, even more in some specific situations. So always consider this technique. Always consider including columns from a query in the index. Because of the clustering data principle. The closer the data is, it's faster to be retrieved from the hard drive. Of course, do not use this tool aggressively. Do not use it as a golden rule. First, it requires a lot more memory. Second, it may not be needed. Again, never optimize prematurely. Always first see that there is a bottleneck, that the bottleneck is coming from the query itself, and then optimize it. And then add all the query columns in the index. Because also this clusterization slows down the CRUD operations, as we already said earlier, and that's a problem. So if you have a lot of updates, including more columns, we'll need more tree rebalancing, and that's not what we want. The middle ground is to include the columns one by one until you're satisfied with your performance, only if you have a bottleneck in the first place. Use it as a last resort. Use the clusterization as a last resort. Include the columns only if you don't have any other option. And consider dropping indexes when you make a lot of updates or a lot of inserts. Other thing you can do, but that's a very advanced approach and I don't recommend it for typical web applications, is to remove the primary key clustered index. So if you want to fine-tune the performance of your table, you can remove the clustered index and add only the indexes your application needs. So removing all the indexes from a table and then adding and fine-tuning all the indexes you need. This is super advanced approach. I don't recommend it for your normal web application. You don't need to have to do that. But you may read about that the clustered index is a problem of the SQL Server performance and so on, but it doesn't matter that much in your average web application. It's an advanced approach. Again, use it as a last resort. Let's talk about some indexing myths. The first myth, and this is a huge myth, is that indexes can degenerate. That's really huge myth. That in time, indexes needs to be rebuilt often, because after a while these indexes become unbalanced. But that's not the case. The database keeps the tree balanced always. So if you rebuild often your indexes, you don't save a lot. What it can do for you, what rebuilding actually does, is reducing the number of nodes in the index if you deleted a lot of data recently or if you inserted a lot of data recently. So this may reduce the memory footprint of the index. It may reduce the hard drive storage, but not its depth, the tree depth. So if there is no tremendous change in the tree depth, the performance will not be improved. So optimization by rebuilding an index is usually 0%. Of course, you may save some memory, but it will be 0% and up to 2% if you did make a lot of insertions or deletions. But 0 to 2% is not that much. If you have a really slow query, rebuilding the index will not improve it. So there is no need to do rebuilding often. That's unnecessary. Don't use it. Another indexing myth is putting the most selective columns first. When you think about indexing, you may think, well, the first part of the filter will remove a lot of the entries because it will filter them. So I'm going to put the most selective column first. But that's not true. The most important part is the column order of the queries. We already talked how indexes are built and how it stores the columns. So if you think about finding and searching through the index, you see that putting the first column of the index as the first filter predicate will be faster than putting the most selective column. This is a myth which exists among developers. So again, design your indexes by your queries and the order of the columns there, and not which column is more selective. That's important. If we have an index like that, which includes two columns, if the second one is more selective and reduces the table more than the first one, we may think that this one should be put first in our index, even though the filter predicate starts with this column. There will be a problem because if we have filtering based first on this column and then on this column, it will be super easy for SQL Server to reduce these two, then these two, and these two, and then filter the rest, which will be a lot smaller, and it will be very easy for SQL Server to do that because it will filter one by one in this column. But if we specify that the filtering to be first on this part of the index, then it needs to scan the whole index here, which is not sorted, and it will be slower for him to scan it because it will need to search through all the records instead of using the tree structure, which will eliminate a lot of records and this essentially is a lot faster. So never consider putting your most selective column first. Always put the index columns in that order in which your filtering works, ordering works, and so on. So it's not about the predicate, how much entries it will filter, but it's about the order of the columns in the predicate. So always consider that as your indexing rule. Here is a similar example for index performance about the column orders. So sometimes it may not be obvious that an index can be improved. So always make sure you check the predicates which are used in the index scans or seeks. If you hover on the execution plan and just hold the mouse there, you will see a predicate text. It's very easy to spot, and you will see what the predicate does, whether it finds the columns by using the index or whether it's searching through all the columns. And if it's searching through all the columns, that's problematic. But if it's searching through the index, that's what index is for. So let's consider this example to understand better. If your query uses two columns, X and Y, to filter data, but the index has key columns X, Z, and Y in this particular order, the query needs to search through the Z columns one by one to find the Y values. And that's a problem, because it will need to go through the Z column, through the whole Z column, to find the Y values. So even though the Y values are indexed and are in a tree, they need to be checked one by one because of the order. Exactly because of the same situation here. Because if the index needs to go through the second column first, then it won't take into account the tree structure, which is based on the first column. So that won't help you. This is why for this situation the index will be searched correctly for X, but then for Y it will search one by one, and that will be slower. You can improve the performance up to 2 times if you reorder the index. So if you put the order in X, Y, Z, then your query searching for X and then by Y will use the index appropriately, and it will not search through the whole it will not search for all of the Y values. So that's important. Again, it's important the order of your queries. If you first search for X and then for Y, then it means that your index need to be ordered the same way to have a better performance, because the opposite will make the database scan through the whole Y table, and this reduces the index performance. Okay guys, thank you for watching this video. I hope you find it helpful. We covered the join operation, we covered the sorting and grouping. These are all advanced scenarios, and you may find them rarely having an impact on your performance, but every time you see a bottleneck in your execution plan for the join operation or for a sorting or grouping, consider all the rules we covered here. Also, keep in mind all the indexing myths, and keep in mind the CRUD operations when you need to change a lot of data. That's the problem. When you need to change a small amount of data, it's completely okay to have indexes. And as a last resort, always consider including more columns in the index if you think that will improve the performance The problem is the CRUD operations here, nothing else. So consider clustering the data too. And the most important rule you need to understand about indexing is that the order of the columns matter the most. So if you have a SQL operation which uses more than one columns, then consider the indexing columns and their order. That's the most important part, because you may add indexes for specific columns, then you may reorder the filter and the columns may not be seeked in the correct order in the index, and that will have a penalty on your performance. So once again, guys, if you have a lot of questions about database indexes, you can ask them down below in the comment section on Patreon, or you may ask them on the Facebook group which I provide, my private communication channel. So thank you guys for now. I hope this was really useful. Bye.